if I'm looking at this worksheet, and I want to look at the 4C, okay? So as we look at 4C, D4C, and we're looking at question number 3. You want to read it for us, Sam? Well, so that we know what we're doing, you know, the question and then part A.
Age is 1 year less than twice Sarah's age. Tony's age is 2 years less than 3 times Sarah's age. Suppose Sarah's age is S years. Write a formula using S.
Okay, so we want to have a formula to find Raj's age, and it said he was what? Go back to that first sentence and read it.
Raj's age is 1 year less than twice Sarah's age.
How do you go 1 less than twice Sarah's age? What does that mean? All right. 2 times Sarah's age and minus 1. That's it, right? It's not 1 minus 2s, right? Remember that phrase less than last year in pre-algebra when you guys looked at rewriting and knowing operations? Less than is always telling you to switch the order, okay? So Raj's age is 1 less than twice Sarah's. And then the second equation says, okay, now we need for part B to write one for Tony's. So if I'm going to write one for Tony's age, Tony should be 2 years less than 3 times Sarah's. So 3 times Sarah minus 2. And the question says, how old are all 3 of them, Sarah, Raj, and Tony, if the sum of their ages, is 21? So I had someone say, oh, so you mean I can put these 2 equal to each other? It doesn't say these 2 people are the same age. It says the sum of all of their ages are 21. So how old is Sarah? Do we have any idea? What variable are we using for Sarah's age? Sarah, right? S. I've used S here for Sarah's age, right? It says use S for Sarah's age, okay? So if I'm looking at Sarah's age, so I have Sarah's plus Raj's age plus Tony's age has to equal 21. And you should definitely do substitution in that you already have Sarah's age, and now you're putting in Raj's and Tony's to equal 21. And you're first going to find out how old Sarah is before you find out anyone else's age. Okay? So if you didn't get that, and if you did do the bonus, and you got the work for the bonus on the back, and not just the answer to the question, but you actually did the bonus work and solved that, put bonus by your name, and if not, I'm just looking at the front. Okay? So what I want for you to do now is turn to your notes. In D6 it says I can solve real-world problems by modeling the situation, and I can interpret the context of it. So, reading problem 1. Kylie, go ahead first.
The local zoo is filling 2 water tanks for the elephant exhibit. 1 water tank contains 50 gallons of water and is filled at a constant rate of 10 gallons of water. The second tank contains 29 gallons of water and is filled at a constant rate of 3 gallons of power. But when will the 2 tanks have the same amount of water?
So if we think of this, this is very much set up to be very nicely written in slope-intercept form, right? The rate of change, okay, that's our slope, and what it started with, 50 gallons, that's our y-intercept. The next one started at 29 gallons, and our rate of change is 3. So if you were solving this, this works out really easy to put y equals to y. We need to know what tank 1 equals tank 2. So we're going to put that first equation, so write that, 10x plus 50 equals 3x plus 29. We're going to subtract our smaller x, 3x, from both sides. And we're going to subtract 50 from both sides at the same time, right? So we got all the x's on this side with 7x. We eliminated our 50 on this side. We don't have our x's on this side. And we are going to have a negative 21. and we divide by 7. And Grace, when I divide by 7, I get x equals -3. So it says, when will the two tanks have the same amount of water? Can we have time be negative? Like, oh, it's just been 10 minutes ago or 15 minutes, or when we think of this problem is impossible. So it says, what constraints must be considered for restrictions on our domain? Remember, time has to be positive. So when we look at this, what we want to put down is this. You want to put x and y cannot be negative values. Those are our constraints. We cannot. So x and y values cannot be negative. We cannot have a negative time. Okay? If we would actually solve this problem with -3, we would have our solution being -3, and you replace -3 up here, and you get 20. And someone said, well, that means that it's 3 hours ago. Yeah, but we're just starting from where they started filling, so will they ever be the same? Not in this situation. So it says, once you've solved a system, the viability must be considered, such as, can we have negative solutions? So as we do some of the problems today, you're going to see that as we solve them, that it's not possible to have that solution. Okay? So, what is viable, the viability of this solution? We can never have time of -3. Just like you can't have a length of -3 feet. When are these two things the same? You can't have negative numbers for those. So sometimes negative does not make sense for our problem, okay, as we are looking at it. So what do you think as you look at that next part down about the United States and you see the map and you see the airplanes and, oh my gosh, you're just like, ah, yeah. So these are the type of problems you're going to see. So, we got the map up there so you can see the wind speed. If you're thinking of flying in an airplane, if you're usually flying with the wind, you go faster or slower? Faster. So if you look at this one, and this one says, if we are looking at this one, we're going, ground speed was 550 miles an hour, versus this one going against the wind, we would say, it's going at 495 miles an hour, right? So if you're going with or against the wind or with or against the current. So anyone ever gone canoeing or kayaking? Okay. If you're going in a river and you're going against the current, you really have to work a lot harder, right? Than if you are going with the current. With the current, it's kind of a, oh yeah, that's really nice. So when we look at these problems, we're going to look at them in terms of both our airplanes, and then we're going to think about boats or anything that would go with the current and against the current. So when a plane travels from west to east coast of the United States, a steady west to east wind acts as a tailwind. That increases the plane's speed relative to the ground. When the plane travels from east to west, we have headwinds. This decreases. So when we are looking, and you're going to be told that something is going with the wind, you're looking at the speed of the airplane plus the wind speed is going to equal what's your ground speed. If you are going against the wind, your speed minus the wind, okay? So here a minus and here a plus, making sure you see those differences. That when we are looking at those, this one is definitely you're adding when you're going with the wind, and here you're always subtracting, okay? Same thing with our boats, if we think of that. When we are going with the current, you're taking your boat and you are adding the current, okay, to get your speed. When you're going against, you're taking your boat speed and you're subtracting whatever the current is. Now, it doesn't seem that bad, and these are actually super, once you get used to writing them, they're really kind of easy to solve. But it's kind of wrapping your head around the going against the wind and with the wind, and people kind of struggle with some of that. So here's our situation on the top of the next page. It says you're traveling from Charlotte to Los Angeles. At the same time, there's another traveling from LA, from Los Angeles to Charlotte. Their speed on each plane is the same, so the planes are going the same. The ground speed is shown in the picture. Model this situation by writing an equation. So, which one of these is going with the wind? A plus W, should this be like 550 or 495? If you're going with the wind, you should be going faster, right? So air plus wind is going to give us 550. And this answer is in miles per hour, so like just in science, you know, where you're thinking about our answer and our labels, we want to have labels with those. When we go against the wind, we're taking our airspeed and minusing W, and we have it equaling 495. Now, if I line these two equations up, which is what I would suggest when you're doing your homework, and we put, so let's kind of just go up above here and solve this right up here. We're going to have the first one, A plus W equals 550. Keeping in mind, some of you forgot when you took the quiz yesterday that A and W means 1. And so like you were making kind of silly mistakes and somebody found it and went back, but that kind of stuff messes people up. And then this one would be our airplane speed minus the wind is equal to 495. This is so perfect for doing what? Elimination. What happens to the wind speed? It cancels. How many A's do you have? And this is where people make the silliest mistake. You have 2A, and I will have so many people say A equals, and they'll add these two together, and they're like, wow, they are going really fast. No, they are not going 1,045 miles an hour, right? You're dividing this, the airplane is not traveling at 1,045 miles an hour. That would be like not any of our airplanes that you're seeing around here, right? So this one, we're going to divide it by 2. And that is how they got the airplane speed being 552, right? 22.5 divided. And is it pretty easy now, if I know that this is 522.5, to just replace that and go, oh, I'm going to take 550 and subtract 522.5? Because it said air plus wind has to equal, and this will tell me my wind speed. Or I could have taken this number and subtracted 522.5 and subtracted 495. That gives me my wind. But the easiest one, I think, is the first one, and you get 27.5. Okay? And you're just substituting it back in. But these are so perfect for elimination because you're going to have a plus W and a minus W anytime you do these. But it's just setting up the problems that sometimes seems to confuse people. So let's look at this next one. We are in a canoe or kayak and we're rowing upstream at a speed of 2 miles an hour. We travel that same distance downstream at 5 miles an hour. What would be your rowing speed in still water? So if you were sitting out on a lake maybe and you didn't have a current, your rowing speed. And what would be the speed of the current? So we need 2 things. We need the speed of rowing, so we're going to go rowing plus the current and our rowing minus the current. Okay? So R plus C and R minus C. Okay? This is our current. This is our, as we are looking at it. When we are going with the current, we went 5 miles per hour. When we went against the current, we were going 2 miles per hour. It is set up again perfect to use elimination. Solve it, please, so that you can tell me the upstream, the downstream. Those are our equations here. And then we can look at our solution. Check with your shoulder partner on your boat speed and your current speed. And they both should have came up as decimals. And make sure you label the answer. Right? They're so nice to add together. If I am adding them together, Noah, what did you end up for we should have had maybe first 2B when you added them, right? Or 2 times the rowing or the boat equaled what? 7. And our boat was going at what? Miles per hour. And then if I am looking at it, what did I have for my current? 7. Okay, so let's go back. This might be the easiest one to substitute into, right? My rowing or my boat is 3.5 plus the current has to equal 5. So I'm going to replace the speed of the boat and I'm going to subtract 3.5 from both sides and get what? Does it make sense we can't have 7?
Yeah.
We got to take 5 minus 3.5 and get
1.5.
1.5 miles per hour. Okay? This is the type of problem, and this mixture type of problem we're going to look at next, that I will often have students, don't go anywhere yet, that will often have students go, when are we really ever going to use this? And as you are looking at this, I did have a student a couple of years ago whose sister was like in pharmaceutical school, and she was like, she has to do this all the time. You're always mixing different things together to get the creams or to get the solutions that people need as you are looking at those. So we'll look at this. We have 2 more problems that we need to look at before we're solving a mixture problem. In the chemistry lab, you have 2 types of vinegar. One is made of 5% of this acid, 95% water, and the other is stronger with 6.5% of the acid. It says you want to mix them together so that you have 200 milliliters of vinegar at a 6% acid. Okay? How many milliliters of each type of vinegar do you need to mix with it? So it says for mixture problems, you want to write an equation to get that final amount. The other equation is with the percent. So it's kind of like when we did our standard form and we said, oh, this is the number of people buying tickets, right? And then the value of it. So it's kind of like those problems that you're looking at, in that one deals with the final amount that you want to get and the other deals with all the percentages. Okay? And it says each part, it says in the same that the first one, except each part is multiplied by the appropriate percent, and we are always going to change our percent to a decimal. So if I am thinking that x is going to be my variable, and I say x is the 5% solution, okay? And I'm going to try and figure out how much of that 5% solution. So please write x equals 5%. Y is going to be our other percent that's acid, which was 6.5% solution. And at the end, we need to know how many milliliters of each one we are working with, right? So our main goal is we need to find, oh, we're going to have this many milliliters of 5%, and we need to have this many milliliters of 6.5%. So the first thing is we are just mixing our 2 things together to get how many milliliters. X plus y has to be how many in our final solution? How many milliliters? 200. X plus y equals 200. It's kind of like saying, you know, we have adult and children tickets. We have 200 of them, right? You can only sell adult or children. No senior citizen discount ones, right? So in this case, we now want to look at what is the percent of x. And we want to not write 5%. We want to write that as a decimal. So 5% as a decimal is going to be 0.05x plus, what is the percent of y? 0.065y. Remember, changing a percent to a decimal, you're moving the decimal over 2 places. Okay? Equals our final solution. What percent do we want it to be? 0.06, right? Times how many milliliters? Because this is our milliliters of the 6.5. This is our milliliters. So times 200 here. So 0.6 times 200. I think we're going to rewrite this equation here.
Is it 0.06?
It is 0.06. Thank you. 0.06. 0.06 times 200 gives us 12, right? So if we wanted to rewrite this equation, this is really 0.05x plus 0.065y equals 12. Substitution or elimination? What do you think? Some ugly multiplying to get elimination. I probably would go with substitution. I probably would look and say, you know what, I'm going to solve either for x or y here because they both have a 1 in front of them. And I would maybe, and it doesn't matter which one, so maybe I just decide, you know what, I'm going to tell what x equals. X is going to equal 200 minus y. And now in this equation, I'm going to replace this x with 200 minus y. So I have 0.5 times 200 minus y plus 0.05 0.065y equals 12. So we're going to distribute. We want to use our calculator. 0.05 times 200. We are writing that. I should have 10. Minus 0.05 y plus 0.065 y equals 12. Now, for a lot of you, when you add these like terms at that same step, you actually could, at this point, subtract 10 from both sides of your equal sign. So we get 2 equals. If I have 0.065 minus 0.05y, that leaves us with 0.015y. Do you agree? Making sense, kind of? We added those. This is actually a negative, right? It was a minus, okay? So we're subtracting those. So at this point, Lauren, what would you do to finish solving?
Divide each side by 0.0.
And when you divide a whole number by a decimal, it should get quite a bit larger. And that makes sense because our 2 had to add to 200. And so when you divide by 0.015, and you definitely do want your calculators for this. What did we get for our y? 0.3 repeating, 133.3 repeating. 133 1/3, we could say, milliliters, right? That is going to be of our, that was what y was equal to. So when we were looking at that, if we were, these are the 2 equations, if you want to write them in. This is the amount one that we had here. This was the percent one. I don't know if you need to write it in the boxes. But we can start our solution. Our solution was, right now we have y. We have 133 1/3 milliliters of 6.5% solution. We need to find the x. Again, I think this equation is the easiest one to put it in, right? Take 200 and subtract 133 1/3. 133.3. If we are doing that, taking to find x, x is equal to 200 minus this 133 1/3, we should get x equals 66 2/3 milliliters of 5% solution. Now, some of you aren't writing. Maybe you like to go back better online and check the notes out and fill them in there. But as you are looking at this, making sure that this is kind of making sense to you. Even sometimes going back over, and there are a ton of YouTube videos on these kind of percent systems, okay? Or solving percent mixture problems, if you put that in. And you'll see many different people explaining it. So if you don't get it this first time through this, don't think, oh, I can't do this, just go back and watch this part of the video over from class today. Or put in a YouTube and see on Khan Academy how someone's explaining it, or someone else. And hopefully after seeing it a few times, it'll make a little more sense to you. Sometimes the first time it doesn't, it's not always as clear, okay? So, the last type of problem that you're gonna see, that we're gonna be working on for story problems before we get into our last part of the notes, is a break-even point. So, what is a break-even point? For a business, it's a point to when income and expenses are equal, okay? So, at this point right here, my expenses are equal to my income. So when we write our linear systems, and there's questions on the test, like if it says that kind of in your notes, I think on this last couple ones, it said, right towards the bottom, it said, there's one like this on your test, and the bottom of this mixture problem as we get ready, there's one like this on your test, and you're looking at this one, and I believe there's one like this on your test. So you will see these on your test. Very similar problems, just a little different situations. It says a linear system is needed to solve a problem like this. You need one equation to represent the income. So when you do this, what we're trying to do is we're going to try and put our income equal to our expenses. That's going to be the key thing. So you're going to have one equation that says income, I equals, and the other one is going to be the expenses, okay? So we, when we write this, it says, you don't need to solve this one, just write the system today, because they show us the answer here, okay? Could you go through and solve it if you'd like to? Yes. So a fashion designer makes and sells hats. The material for each hat costs $5.50. She sells the hats at $12.50. And she spends $1,400 on advertising. How many hats must she sell to break even? So, first thing we want to look at is, what is our income? So, I is going to equal our income. I'm going to put income equals, that's my I. How much income are we making? Where does she make her money? When she sells the hats for how much? 12.5 H, right? Now we want to look at our expenses. So this is where it costs her money. It's costing her how much to do this? It's costing her, for each hat, costs her $5.50 a hat, right? Plus, she's also spent how much money on advertising? $1,400. This is so perfect to set and use our substitution. And it tells us, put income equal to expense. Okay? 1250H, 5.5H, plus 1,400. You subtract your 5.5, right? So 12 minus 5.5. We would have been looking at 7. H equals 1,400. Can we find out? We find out what H is. Have we figured out what our expenses are? If we just find H by dividing this by 7. We have only found out, right, at this point, one of our break-even hats, right? We figured out that we need how many hats to break even? 200. So how many hats must the designer sell to break even? We must sell 200 hats to break even. Do we know how much money that is? How would you find that much? Would be the easiest equation to use. First or second? First one. Plug in 1250 times 200, right? So this point right here, this break-even point, is located at 200 hats. And if we are looking at it, what do we get for our second point when you substitute that in? We should have had 200 hats for our solutions. Anyone figure out our cost? So, and that break-even point for our income, how much money it was, say it one more time, Avery? $2,500. Okay. As you are looking at your homework, we are doing page 190. I just want you to know that on page 190, we are working on this today and tomorrow, and then you're going to get your worksheet. And I would say that by Friday, you should have the book assignment done, okay? So tomorrow, we're going to get the worksheet, and we're going to kind of go through some equations and setting them up. And those of you using books, I don't want them taken with you. Because there's a bunch that are left out in your team center that your teachers keep bringing to me because they're like, oh. So if you're using a book, just return it. So